Here's part 2 of our notes on nuclear equations. We're going to be working on the processes of fission, fusion, and talking about half-life and how to work those types of problems. So to begin with, we ended up last time talking about alpha decay, which is where a particle breaks down and it, through a process of fission, making a helium nucleus. And it will reduce the atomic mass of what you started with by 4, and it reduces the atomic number by 2. Then we went over beta decay, which is really, it's a neutron changing into a proton plus an electron. The mass doesn't change when this transmutation, there's the fancy word for it, occurs. The only thing it changes is you get another proton, so you get a new element formed. Talked about gamma radiation, and for us in class there's really no calculations to do for that. When a gamma particle is released, it's just it happens in some forms of nuclear reactions, fission reactions, and it's usually associated with something else, but you get a very high energy particle gamma ray. So we're on section D as in dog now, and this will be strength of penetration of these alpha, beta, and gamma particles. You can reference page 802 of your textbook. You'll have this diagram. It's on last night's homework. Strength of penetration of particles. So what we're going to do is we're going to label our alpha particle. We'll do a beta particle here, and then gamma particle here. This is going from lower energy to higher energy. And we're going to draw a little barricade separating these. So we'll say that's a piece of paper. And then we'll say this here is a piece of, well, like cardboard. We'll do little corrugations in there, but something like that. Cardboard. Or it could even be like maybe a piece of aluminum foil. Something, just a really thin piece of material. And then at the end, we're going to sit there over here and draw like a piece of cement, or perhaps it's lead shielding, some piece of lead. So what'll happen is an alpha particle, make the little fancy A here, an alpha particle, which is the helium nucleus, it doesn't have a lot of energy. It can be stopped by just a piece of paper. Now a beta particle, can go right through a piece of paper, but something a little thicker, a piece of aluminum foil, make a fancy looking B there. So a beta particle can be stopped by a little bit thicker piece of material. And then highest energy, if we're emitting, if having a radiation source, gamma particles can go right through, gamma rays right through these materials. In fact, if you've ever had a dental x-ray, do you ever notice that when they will cover you up in a piece of lead apron, and then the technician walks around the room and hides behind a wall that either has lead or probably nowadays a very thick piece of cement to protect themselves from the radiation that's coming through from that. And this is gamma, okay, kind of the fancy way, gamma radiation. So it takes a thick piece of material to stop that. So alpha particles, not much energy to stop them, a piece of paper, to gamma particles, super high energy. Now we're going to go to part E. And let's see, I'll change colors here. Part E. This is going to be fission versus fusion. Fission, F-I-S-S-I-O-N, versus fusion. These are two nuclear processes. One is a process of splitting in half, what we've been or breaking it into smaller pieces, and then fusion is the opposite, is building something big. So number one, under this, fusion is, well, let's write it. We'll start with that definition. In houses, you have electric fuses, even in your cars. That is to connect two things together. Well, fusion, this is small atoms joining into larger atoms. small atoms or even particles, small atoms joining into larger atoms. Draw a diagram. In stars, you usually start off with 4 hydrogen atoms. So these would be atoms of hydrogen. And with extremely high temperature, also there can be high pressure as well. You're really cores of stars. What can happen is these can be clumped together, various reactions will occur, but what will happen is those will end up forming a larger atom of helium. Now, when all these particles are shoved together into helium, it's going to release some energy. So we're going to say plus energy. A little bit of the particles that were in here, the super subatomic particles, get converted into pure energy. And with fusion reactions, these are the highest energy output. In the world of nuclear bombs, you can have, the standard nuclear bomb that goes off. It's a fission process. You get a big chunk of like uranium, and then it breaks apart, releasing energy. If you make it go through, if you use a nuclear bomb to detonate a hydrogen bomb, it turns it into a fusion bomb, which produces a lot more energy. Okay, that's not the, oh, and this is how stars are powered. I'm going to call this star power. Once we figured out, what science figured out, that stars were powered by nuclear fusion, it made total sense how really that was the key to opening the really understanding of outer space for us. Because up to then, they didn't really know what was doing that. Okay, the next one. Let me see, do I have a page number here for you? On that one I don't, that's in your book. Probably about page 810. So now the next one we're going to go over here is going to be fission. So this will be number 2 under here. So let's see, number 2, fission. So it sounds like you're going fission, but there's 2 S's, F-I-S-S-I-O-N. And what I like to do is, I was just kind of, whenever I see the word fission, I just imagine I'm splitting right down the middle of the 2 S's, because that's what fission is. It's when large atoms split into smaller atoms. Large atoms split into smaller atoms. Oops, sorry, let's make that 1 T in atoms. So an example could be, like with a lot of nuclear power, let's start with uranium-238. That's its mass, 238. Uranium has 92 protons. Well, it will go through a fission reaction to make krypton-91. Krypton's 36. It'll also form a large atom of barium, barium-142, with 56 protons, and then a lot of energy. So this is how nuclear power plants work. Also, nuclear bombs. You take a big amount of either uranium, or even if you want higher yields, you use plutonium. You allow them to get, these atoms to get close to each other, because they're shooting protons. They're losing protons constantly. You put them close together, a chain reaction occurs, and in a nuclear bomb, it happens almost instantly. You get a lot of energy produced. In a nuclear power plant, they slow it down quite a bit. So I guess you could say a simple diagram would be something like this. You start with a big atom of uranium, and then it's split into a smaller atom of krypton and a slightly bigger atom of barium, plus you get some energy. And so this would be nuclear bombs and power plants. The problem is, with both of these processes, you get energy out of it, but these are highly radioactive, and they can be radioactive for millions of years. And want to talk about number 3 here. Okay, this process would be called splitting the atom. And number 3, energy. This is Einstein's famous equation. Energy is equal to the mass of an object. Mass would be measured here in kilograms. Energy is actually measured in a unit called a joule. We'll use a capital J for that. But you saw joules when we talked about how many kilojoules there were for ionization energy. But energy is equal to mass times a constant that Einstein called it. Well, it turns out the constant is the speed of light, which turns out to be a fairly large number. 300,000 works out in one form to be kilometers per second. But you take the mass, you multiply it by this constant, which will, but then you have to square the constant. So it's 300,000 times 300,000 times whatever the mass is. Okay, we'll just say that's the speed of light, by the way. Turns out Einstein kind of predicted it would be, and they did measurements in speed of light. That's kind of like the constant of the universe. So his famous equation, the relativity equation, energy is related to, equals, mass times a constant squared. And then we found out that that constant became, oh, sorry about that. Let me scoot that up for you. So E equals mc squared. Energy is related to mass times a constant. So that's where we get the energy out of nuclear power plants. The problem with nuclear energy, there's highly radioactive waste stuff that we've got to deal with for thousands of years. That's a big issue. And let's see, I've only got 3 minutes left, so we're going to do part F. Part F here. Set this aside. Okay, part F, and really the crux of today is the rate of decay. Rate of nuclear decay. That's how fast something is breaking down. And they measure these particles that are radioactive. They use a term called half-life. I mentioned this before in a previous unit. And half-life is the time it takes for half of a radioactive isotope to fission decay into a smaller one. So, the time it takes for half of a radioactive isotope to fission decay into smaller atoms. To fission, I'm going to put a fission decay into a smaller atom, or into smaller atoms. So this is a measurement. Scientists they'll get some radioactive material. They know how much of the material's there by doing various measurements. And then when time goes by, they can come back and measure how much of that original radioactive material is left. Carbon-14 is a great example. We can use it to, in fact, that's what our example is. So let's put over here, now let's do an example for carbon-14. So we have carbon isotope 14. And what will happen is, we're going to put a long arrow here, make this kind of long. It's what we'll call T half. Its half-life time is 5,730 years. We saw this before in a previous assignment. And so it'll take that long for half of this carbon-14, whatever the mass is we have, it'll convert itself into nitrogen-14. It probably looks like this is probably, in this kind of example, we're going through a beta decay because we got the same mass, just increase the number here. It'll also kick off, okay, there's our electron that we talked about with beta decay. So it takes 5,730 years for half the amount of carbon-13 you start with to break down. So let's give a little diagram of this. Let's say you've got, let's draw a square, give yourself some room here. And we've got 100 grams of carbon-14. How long is it going to take? I'm just going to put some dots in there. You can shade it in. So there's carbon-14. Its half-life is 5,730 years. So after that amount of time, when we go to if we were to reanalyze that chunk, we would find that half of it is carbon-14. Okay, this is carbon-14 there. The other half has become nitrogen-14. I'll just put N-14. This here is still carbon-14. So we only have, of our original 50 grams of carbon-14, after its first half-life, we'd only have 50 grams left. And these are the types of problems we'll be giving you. After another half-life for this, 5,730 years, we're going to end up with half of this, what we started with. So let's see. We had 50 grams, so half of 50, we're going to end up with just 25 grams of carbon-14. 25 grams of carbon-14. And then all this other stuff here, this is going to be nitrogen-14. So we're going to end up with probably 75 grams of nitrogen-14. And we'll do one more here. One more half-life, 5,730 years. At some point, let's see here. So I'm going to just draw, there's where we were before. So we're going to have about half of this left. So this will be carbon-14. The rest of this is all going to stay nitrogen-14, which is stable. So, way to look at it, over here, when we first started this process, when we started with our original sample, we can say we had 100% or 1/1 of the original material. After one half-life, we had half of the original carbon-14 left before. At the end of the next half-life cycle, we had 1/4 of the original carbon-14 left. And at the end of the after a third half-life, we end up with 1/8 of the original carbon-14 in there. So we're going to put amount, that's an abbreviation for amount of carbon-14 remaining. So this is a way that when nuclear fission reactions occur, we can record how fast the process is by how much of the stuff breaks down. Well, I've got some more notes here, but I'm at my limit now, so I'm going to stop, and we'll get that at a different time.